Thanks, Frank. Good afternoon, everyone. If you didn't hear it the first time, I'm Robin Matram, the Emeritus Kernow Professor of Engineering here at the University of Melbourne. I'm standing in today for Michael Breer, who's the Director of the Melbourne Energy Institute, and I'd like to welcome you all to this MEI networking seminar. Before we begin, I acknowledge that today we're gathered on the lands of the Wurundjeri people. We're in fact in a building which the design of the building having been very impacted by consultation with their elders. And that's a topic, happy to talk about it afterwards with people. So thank you for joining us today for the fourth installment of the MEI Network Seminar series with a focus on energy commodities. And here's what's coming up. So first of all, a bit of housekeeping. I'm reading from a script here for our online audience. If you have any questions, please enter them into the Q&A box as the chat function is disabled. We'll have some time at the end of Mohan's presentation to get stuck into Q&A. And we'll endeavour to get through as many as we can. So let me now introduce our speaker, Mohan Yellishetty from Monash University. I've known him for many years and we've worked together a little bit, and I have the highest respect for him as someone who actually can spell the words when it comes to energy commodities and critical minerals. He's been working in this area for some time. He's one of the best collaborators that you can find. He just goes around and is prepared to share what he's doing with others. That's actually something which I'd commend to everyone. You can get more done when you work with others. He's extremely good at that. He has a lot of collaborations with India and indeed is poised, I think, to bring in some more. So I'm not going to steal any of your thunder. I hope I've given you a good enough wrap here. He is co-founder of the Critical Minerals Consortium at Monash University, and I know he'll talk a little bit about that. So over to you, Mohan. Oh, you're mic'd up.
Thank you, Professor Robin Matram, for that wonderful Sorry, all those joining online. My apologies that I did not turn on my microphone, but yeah, I did not talk much, but just to acknowledge the country, etc. Thanks, Franca, for reminding that. Yeah, so yeah, that's a kind of overview of my presentation. Talk about the demand drivers and the clean energy metals and the production versus processing, some of the pinch points, some of the issues in terms of where they are produced, where they are processed. And that's exactly one of the reasons why we are talking about it. And then I will also present a way forward and where Australia can play a huge part in trying to de-risk some of these supply chains, because they are very, very important to fast track the climate change targets that we have set for ourselves. And yeah, some of the important mining transitions, because I'm a very proud mining engineer with 30 years experience in the industry, have seen a number of these transitions myself. So they are some of my personal reflections, and then talking about substitution and recycling. But anyway, with some final thoughts. So before we start, again, as I said, I co-founded Critical Minerals Consortium with Professor David Whittle, who is here in this room, and also one of the champions. I call him as my guru and the guru of minerals, Professor Gavin Mudd from RMIT University, and my other colleague from Monash University, Stuart Walsh. And we are blessed to have some of the spectacular brains, I know two of them here, Professor Batterham himself, and Mr. Stephen McIntosh, who was former Chief Technology Officer at Rio Tinto, and who keep on advising us on a number of things that we do, and so on. So we started to bring a number of different people with different areas of expertise together, mainly to assist the national and international policymakers to see what best can be done to progress in the direction that everyone wants to progress. So it has got academic colleagues from a number of universities and also CSIRO to start off. Now we are in the process of expansion mode, where we are trying to have partnerships with industries and international partners to make the impact. So at Critical Minerals Consortium, as Professor Batterham said, we have been doing pioneering work. Especially my own specialty was when I came back from Yale University after my sabbatical back in 2014 in Professor Tom Gradle's group, which was considered as one of the pioneering groups in critical minerals methodology development. I recruited a PhD student, Eric Yuan-Ye, who currently works for Victoria Police, because he's a data scientist, to develop a model which is more agent-based, because the Yale model is more about a very static model, which is not, which uses multi-criteria based analysis to identify which mineral is going to be critical for which sovereign entity, which is like, it gives you steady state at any given point in time if you want to understand which mineral is critical, so that can tell you accurately. But whereas we proposed this new model, which is more agent-based, which will understand the dynamics between producers, consumers, and also the other important stakeholders like governments. For example, critical minerals is all about, when government's involved, that's where it tends to become more critical. And we have done a number of other bits and pieces. For example, this was one of the seminal studies that was commissioned by Geoscience Australia. And that also had a number of recommendations, and then they were taken up by the GA later on. So this was the model that I was talking about. So you've got mineral suppliers, minerals consumers, and regulators and others. So which is more, as I said, it's more dynamic. So because any of these keeps changing, so that's when our model is more robust enough to understand those nitty-gritties and see how the mineral criticality is going to change from different sovereign entities' point of view or different companies' point of view. Then this is the report that I was saying, where we were also partnering with Geoscience Australia and RMIT. So we made several recommendations, but one of the most important and significant recommendation in this report was we have got a lot of tailings and abandoned mines. So we proposed that tailings be sampled to ascertain what potential they have for critical minerals extraction. That means you're trying to give them a rebirth, a second life. So that's one of the recommendations which later got funded. Initially, it was through the Exploring for the Future program, and which was mainly to explore Northern Australia and Northern Australia, but it also funded a program which was linked to the exploring for looking at number of tailings and etc. And however, I was not involved in that project, but it was my colleague, Professor Gavin Mudd, and also the UQ and government of Queensland were the party. But we are also, as a kind of consortium, we were also providing a lot of advisory, a lot of thought leadership in this area. In that we have been coming up with white papers to submit to different inquiries. And for example, this was one of the white papers that we submitted to the implications of COVID-19 pandemic for Australia's foreign affairs, defense and trade. It's a parliamentary inquiry, and then we testified. We submitted the white paper, and also we testified before the committee. And one of the important thing that this particular paper revealed is, although Australia is considered as a supplier of many critical raw materials, but we are also at a danger of getting some of the important critical raw materials for our own use being disrupted, in that mainly we were talking about potash, which is main ingredient for agriculture sector. So then we also conducted a stakeholder workshop, which was again in response to the Critical Minerals Strategy 2023. So then we made several recommendations to this also, and some of the recommendations are listed here, which you can look at. Okay, now let's get into the subject specific. It is always good to start off with a picture. So as you say, so don't move, I'll fill you with full of 98% of lead, 1% antimony, 0.75% of silver, and 200 parts per million of nickel. So you're talking of a bullet. So as you would understand, antimony, lead, and perhaps nickel, we are talking, they are part of critical minerals. So it talks quite a lot about what we are going to discuss today. So when it comes to critical minerals, they are very, very important for number of different technologies, whether it is solar panels, whether it is electric vehicles, or whether it is wind turbines, whether it is also the medical and medical technology kind of equipment, and also for defense and strategic purposes, because they possess certain specific characteristics. For example, they are very catalytic in a sense. If you look at most of the rare earths, about 75% of the rare earths are used as catalysts in a number of different components that are manufactured today. But also, for example, you have neodymium, praseodymium, and terbium, and those are some of the magnetic kind of rare earths. And then you have luminescent, for example, indium, germanium, gallium. They are of those characteristics. And what is most important, I think I like this particular metal wheel as much. It talks a lot about a number of things that we do or we have been doing for so long. So when I was at a mining school, pretty much I was learning about some of these mainstream metals. We call them as, the main metals of interest: copper, lead, zinc. Some of them are base metals, some of them are precious metals, and they are very, very important underpinnings for our modern civilizations, right, for so long. What happened is, if you look at the ore genesis, for example, those geologist colleagues will appreciate, you've got orogenic, you've got IOCG, iron oxide, copper, gold kind of deposits, which is Olympic Dam, and sediment hosted deposits. So they all have specific signatures they carry with themselves. So that means whenever you are talking of, for example, if you look at Olympic Dam, which is into that kind of iron oxide, copper, gold kind of deposit, would have number of other metals which we never sort of cared for, or which we were never interested in, maybe 15, 20 years ago. What happened as a result of that is we were only interested in the mainstream metals, and rest got discarded into tailings storage facilities. And later part of my talk, we'll talk about my other part of research, where we try to map the entire country, and we discovered that there are about 80,000 disused or abandoned mine sites in the country, so which could perhaps come to greater use when you're talking of critical minerals and the supply chains. But I want to draw your attention to the 4 or 5 important candidates, which are again in the news for all good and bad reasons in the last couple of weeks. For example, if you look at germanium and gallium, and these are the 2 metals that I researched when I was spending my research sabbatical at Yale University back in 2014, alongside antimony, which is also very important. And there's only one single antimony mine in the country, and that's in Victoria, in the coastal field. So gallium and germanium supplies are now restricted, because China want to have them for their own domestic requirements, because everyone is trying to chase, and because they are very important building blocks for a number of critical technologies that we are trying to build today. So look at gallium as an example. Today, 100% gallium is extracted as a byproduct of, for example, bauxite mining. You've got a red mud, and red mud contains majority of the gallium. And if you look at average concentrations of gallium is about 50 ppm. That's a kind of cutoff grade for extraction of gallium. And same with selenium and tellurium. Gallium arsenide is used in, again, solar photovoltaics. And then same with cadmium telluride, for example. They're all very, very important underpinnings when it comes to solar photovoltaics or solar cells, etc., manufacturing. And same with indium. All of them are very, very crucial. So they are extracted as byproducts, not as the main metal of interest. So as you go from the inner circle to outer circle, that shows the degree of dependence of these metals extraction. And that's a scale that you're looking at, 100% being 100% to being 0. And the other important metal that I was talking about is tellurium, which is again extracted as a byproduct of copper slimes worldwide, if you look at. So I don't have to overemphasize the significance or importance of some of these critical metals, or metals for that matter. If you look at a simple printed circuit board that is part of any electronic gadget that you use, for example, mobile phone today is a pack of 45 metals, we say, right? So if you look at 1980s, it consisted of about 11 elements. And by the turn of 1990s, you got 4 got added. And now, you got over 45 of metals that make up, or metals or mineral derived products that make up a typical PCB that you have in laptop or any kind of gadgets that we use. So that means their importance is becoming very significant. So when we talk about critical minerals, there are 2 important things that we, and this is one of the seminal kind of approaches, or kind of methodologies where people said, a mineral is deemed to be critical if there is a risk of supply disruption, and that supply disruption could have enormous or tremendous consequences on national economy or to a particular industry sector, and so on and so forth. So this was proposed, I think this was 2008, National Research Council, they proposed that kind of metrics, two-dimensional metrics, where people would say, what is the impact of supply disruption and what is the level of supply risk of a particular metal? And then you position that. And if you look at some of them, they are highly sitting at supply risk, and also their disruption, that disruption would have enormous consequence on industry sectors, for example. So that was one of the seminal kind of, methodologies that was proposed. But later on, there were a number of other kind of methods that have been in use. For example, as I said, Yale methodology and our own methodology of agent-based methodology. So that's, we just talked about the science and economics of critical minerals, but look at this. This is the most important and significant aspect of critical minerals, and that's geopolitics. Look at this, which is slightly dated, maybe 2 years back, but still the picture doesn't change too much. So irrespective of where metals are mined, the significant portion of processing happens in China. And again, for all valid reasons, China want to produce them because they've got a huge manufacturing base and for their own consumption and so on. But also in a situation like, for example, if you look at the first ever kind of signal that came to world was in 2010, when China and Japan were in a kind of dispute with about a small piece of land, some territorial dispute, and then China sort of stopped supply of rare earths, and that's when the first kind of supply disruption happened. And there were a number of such instances where supply disruptions have happened, and the recent one is about gallium and germanium, which are very, very crucial ingredients for the semiconductor industry. That means semiconductor industry would be in short supply of some of these two important ingredients. And if you look at rare earths, for example, China produces about 60% of rare earths in China, but whereas they process about 80% of world's rare earths, and same happens to a number of other commodities. As you would see, when you have heavy reliance on one geographical location, you could have a number of consequences. And if you look at 2020 also, gallium as a commodity, the prices have sharply risen, not because China wanted to control it. The province in which bauxite mining used to occur in China was experiencing heavy floods, and also some environmental restrictions have come into force. And thereby, because the bauxite production has gone down, so gallium also was produced less. So which means the price, people had to pay price premium to secure the supplies of gallium, for example, for that year. And these could happen as we are living in a very fragile geopolitical kind of setting. Such disruptions could be forthcoming a number of times. And I would recommend that you read this article by Professor Louis Wells from Harvard University. He talks about the geopolitics. It's not only China does it. Everyone, whoever were in control of minerals, always did that. So whether it was Germans at some stage, Japanese at some stage. So that's a very common thing. So today we are talking about critical minerals, which are of energy importance. So they could be sort of grouped into three main functional areas. One could be batteries, electric vehicles, and electrification. So critical minerals can be bunched into the three different categories. And you've got many of them somewhat related to, the energy transition story that we are all talking or listening almost every day. And if you look at, there are many studies which said out of 90 naturally occurring elements, about 75% have been identified, 75 minerals have been identified as needing by 25 sovereign entities as critical. And out of that 75, about 40 to 50 of them are going to be needed for mainly energy transition. That means, there is a huge requirement of many of these commodities as we accelerate our climate change mitigation. So this is, again, an excellent periodic table so as I said, about 90 naturally, out of 90 naturally occurring elements, 75 have been identified by 25 sovereign entities as critical to their economies. So if you look at this, it presents EU critical minerals and the minerals mined in 1950. So as you would see, there are many of them now critical to the European Union's kind of energy transition story. So that means many of them were mined, but what happened is we just discarded without extracting that additional value because we didn't find enough use of these metals back then. So perhaps they're all sitting in a number of tailings dams, etc. Again, when it comes to renewable energy and the main demand drivers, as you would see, if you look at solar photovoltaics and then onshore wind and offshore wind. So look at the mineral or material intensity of these technologies. So everything is pretty much underpinned by availability of some of them. So as you would see, that's why nowadays, you read a lot about copper as the next generation of gold, now because copper is pretty much part of every technology that we are speaking today. And when you look at typically solar and wind together constitutes about 10 to 12% of world's energy production. And so that's a kilograms of metal requirement for a megawatt, kind of energy that we produce. And as we all know, a typical electric car requires 6 times as much minerals compared to their IC engine counterparts. So that means the metal intensity is surely growing, but also that means that's for a good reason. If you look at on the right hand side, we have got tons of carbon dioxide equivalents, and that's life cycle emissions of vehicles. When you look at battery vehicles contribute, only almost 50% less compared to the IC engine counterparts. And that too, when you look at the significant portion of the GHG emissions are because of the energy, because currently our energy that we use, the electricity that we use is predominantly fossil fuel kind of, energy mix with only maybe up to 20-25% renewables. So should that change to 50%, that would be halving, almost half of what we have currently. So that's a significant story that is compelling for everyone to sort of electrify, trying to transition to that kind of thing. Sorry. So what does that offer to Australia? So Australia has got significant resources or reserves of number of these critical commodities, which are very, very vital to the energy transition story that everyone is speaking, and the climate change mitigation story. So if you look at, we produce nearly, we are the largest lithium producers, right? About world's 50% of lithium is produced in Australia. But what we do is 1% of lithium as spodumene, and then you concentrate it to 6% and then ship it out. And then all of the downstream processing, as I said in the previous thing, that happens in China. And that's where about 90% of the concentration in processed lithium, lithium hydroxide or lithium carbonate, is controlled by China. And again, for all reasons that they need some of these important minerals for their own climate change targets as well. So, but there also could be a lot of the geopolitics that can be at play. And likewise, we are number 2 as far as vanadium resources are concerned, cobalt, the same, manganese, graphite. So majority of the critical minerals that we just looked at in the couple of slides previously, they are abundantly available in Australia. And yeah, there are, almost the full map is full of that. And this is even more, striking as you would realize, if you look at country reserves of different battery metals as a percentage of global reserves, right? As you would see, Australia sits pretty comfortable on number of these metals, but whereas other countries, they don't have. And we could play a major role in producing them, processing them, and supplying to different markets because they're going to be needed. So we are in a very fortunate position to be able to have majority of these critical commodities that world needs, but we derive the least value out of some of this extraordinary endowment of minerals that we have. And as you would see, especially if you look at here, what you're talking about is the production and processing that I said. For example, we produce about 50% lithium, but what happens? We just ship it out, and about 60 to 70% of their processing happens in China. And likewise, you name any particular commodity of your interest, irrespective of where they are produced. For example, copper, majority of copper is produced in Chile and South American countries. But again, the processing occurs, majority of the processing is happening in China because they have created the infrastructure. So they saw that this boom is going to come, and they invested heavily into these major infrastructure projects where they can do it at a cost and scale that is very competitive. And same as you would see, nickel, Indonesia is one of the main producers, but again, the processing. So as you would see, the pinch points in many metals is the processing, the downstream processing, rather than the mine production itself. Okay, that brings us to the thing that the other part of my research that I do as part of my team is the Resources Trinity. So we also sort of co-founded Resources Trinity in that there are, as I said, we published this first ever national database of all the known occurrences of mines, both operating and abandoned in the country. And we discovered that there are about 80,000 of them sitting idle, doing nothing. There are holes in the ground. Again, they could be small shaft to a big open cut in Latrobe Valley, for example. So, and majority of them are a public safety risk, environmental risk, and so on and so forth. So they are liabilities. And some of the liabilities have been estimated of some mines could be billions of dollars because they have been sitting there in perpetuity and causing a lot of harm and damage to environment, for example. And we also did mapping of all the ash ponds in the country. So that also means that some of this liability can be really converted into an opportunity if we played it well. Because as I said, majority of the mines that were in operation, say 20, 30 years ago. One, the processing wasn't as efficient as it is today, like, the recoveries. Today, we talk of recoveries of 80 to 90%, but back then, perhaps, because of the technology, non-availability of, all of that, perhaps the recovery percentages were slightly lower. That means there is a lot of remnant gold, remnant, cobalt, etc., depending on the ore associations, etc. So that also gives us an opportunity for, recovering some of that remnant metals, and that would compensate some of the mine rehabilitation costs that we'll have to sort of bear with. The other important thing is, as one of the important things, again, my good friend and my colleague, Professor Mudd, is one of these, he has been doing, he's considering himself as a data junkie. So he does a lot of this historical collection of data, and he produces all these fantastic graphs. So in that, what you have is, if you look at production trends of majority of the minerals and metals, they are going exponentially, over time, right? And because again, everything is underpinned by availability of these important metals or minerals. Anything that you cannot produce, that must anything that cannot be naturally grown must be mined. So that's exactly is the philosophy where the production trends are seemingly staggering. So one of the important transition, as I said, I have seen is the grades are declining over time, and that's a trend of how the grades have been declining of different metals, whether it is copper, iron, zinc, lead, gold, etc. And then mineralogy is becoming very complex. As I was having an informal chat with my colleague, Dr. David Whittle, just before the start, and he was in attendance at a conference where one of the BHP colleagues was giving a talk. So if you look at Olympic Dam as an example, Olympic Dam could be second largest rare earth deposit in itself, the tailings of that comes out of Olympic Dam. But the problem is the complex mineralogy. That means, the grain sizes are so tiny. That means, crushing and grinding has to happen to that fineness to be able to separate the metals. And Professor Batterham himself being an expert in mineral processing would appreciate that. So they are becoming from shallow to deep deposit. That means all shallow lying deposits have been almost exhausted, which means we'll have to dig deeper. That means you will have all those complications of geotechnical and stability, etc., etc. And the cost is going tremendously high over a period of time because, again, energy. See, one of the reasons why we cannot produce rare earths onshore, people say many of the times, is we do not have proper infrastructure to support it. Like Linus is now going to set up a factory in Texas because US has given them some 300 million. Because the arguments that people put up is we don't have microgrids, where our energy is quite expensive, and we don't have proper infrastructure where we could do that in-house. And then, as you would see, the waste volumes also have gone up tremendously. As you are going deeper, that means you'll have to move more earth out of the ground, and that means you're stockpiling large amount of wastes that are coming, not only the overburden and waste rock, but also the tailings, because you have declining grades means something else is replacing, so which is mostly the gangue minerals as part of your consistency. And one good thing that is happening in our favor is the mining efficiencies have been terrific. So that's where the step-changing technologies from time to time are able to turn the whole business around and still make this equation work. So this is the outcome of the project that was commissioned by Geoscience Australia, and where I think it was a joint project between RMIT University and Geoscience Australia and the University of Queensland, where which was part of Exploring for the Future program. So the main purpose was to randomly select few tailings dams sitting across the country and then monitor, what could be the potential in them for extraction of critical minerals. So that's where that's where now everyone is sort of looking. And I think this was on one of our papers that I co-authored with Professor Batham, where we were proposing. So when you have got these tailings, which are already finely ground, because in the process of separation, you already ground them, crushed them, etc. So they are sitting in a tailings pond. Even if you are able to extract 50% of the remnant metals, so that is still a valid economic proposition for extraction. Because one, we need to be able to supply enough materials for the energy transition. So that means we have to have a number of different ways in which we extract, because we were at a conference in Perth a few weeks back. People were saying, a lot of industry experts were saying, it takes literally 10 years to stand up a greenfield project in the country. And it is getting even more challenging to, so if that is the kind of scenario that we work, that means it is hard to meet the climate change targets, not only by Australia, but also rest of the world, because world needs these important ingredients that drive these. And yeah, the next important thing is about co-production. I call it as opportunistic co-production. Yes, as we saw previously, for example, gallium as an example. Gallium is extracted as a co-product, not as a main product, when you are extracting aluminum or bauxite. So you got red mud, which is a major waste stream, and when you process through that, that you extract. And same with a number of other important commodities. As you would see, the blues are co-production, and the orange is the main product production for different metals, starting from lithium to a number of those critical minerals. Yeah, so there was a proposal back in 2014, Neister at their Port Perry operations, they were trying to make some small modifications to their existing circuits to tap into some of the important byproduct or hitchhiker or, the co-product metals, for example, germanium and indium in this case, because, if you look at sphalerite, they used to get even in Hobart facility also, they were getting a lot of zinc ores from Century Zinc mine back then, and then they were trying to extract germanium because that's a kind of mineral association that you would have. And then they also had plans for tellurium, antimony, and selenium, palladium, the three important platinum group of metals. Yeah. So last couple of slides. One is substitution and recycling. So now when you don't have, you'll have to, necessity is mother of invention. So people have to find alternative ways to work around. So there are those. And recycling, yes, humans have been terrific in recycling. And if you look at the mainstream metals, copper, aluminum, and so on, we do the best of our abilities. Perhaps that's something that I will talk later, but yeah, so we, as part of the Australia-India Chamber's involvement, we did this, 4 workshops, and then we wrapped up in the form of a report. And one of the things that we said is when one country cannot solve the whole problem, so the best way is to work in collaboration. And that's where we proposed Critical Minerals International Alliance. So that brings to my last slide. These are some of the final thoughts. So as you would see, if you want to make critical raw materials, so simply, you have better transparency, more education, ESG compliance, recycling of legacy waste, and that becomes a simple mineral. So if you take out all those issues around minerals, a critical mineral would eventually become a simple mineral. And yeah, there are some of the important things that perhaps I don't want to sort of read them, but I'm happy to take any questions. Thank you very much for your attention.
I'll get the questions.
Sorry.
Mohan, thank you very much for walking us through. It's not just critical minerals and with an emphasis on energy. One might say it's complicated minerals as well. It is far from a simple topic, but you've highlighted some opportunities there. And thank you very much for that. Let's open for questions and discussion. First of all, anyone here want to throw a question to Mohan? While you're thinking about questions, I'd actually invite you to tell us a little more about the international alliance that you're working on. What countries are involved? What stage is it up to?
Yeah, thank you. And in fact, in this report, Professor Batterham also has a foreword, yeah, we were fortunate to have him advising and mentoring us through the whole process. So as I said, I am also, as part of my other role at Australia-India Chamber, I am national co-convener of Critical Minerals Vertical. So what we said is, if this is a problem faced by so many partners and so many countries, why can't we bring them together and then form an alliance? So because if you look at the critical minerals, Australia has a world-class endowment of critical minerals, like as far as reserves are concerned, but technology is somewhere else. For example, Japanese and Koreans are really good at the downstream processing and technology and the processing and the finished products and so on, assemblies, etc. And markets are elsewhere. For example, India as a country requires huge quantities of these minerals going forward for their energy transition story itself. For example, India they've got an ambitious plan of having 500 gigawatt capacity by 2030. That's the ambitious target. That means almost it translates to 30 gigawatt capacity more than 30 gigawatt capacity per month, which is huge. So they need all of that. Now there is a bit of consensus that is sort of emerging that people have to work together to be able to solve this problem, because no single country is good at everything in the entire value chain or supply chain, for example. So there's one that business to business and government to government. And in fact, if you look at the minerals security partnership led by United States, has got number of member countries like Australia, Korea, Japan, number of European countries. India was recently invited into that. So that happens at a government to government level, but there's also business to business already happening, because now free trade agreement is in place. A lot of companies are investing into into many projects. But also besides that, because of my prime job as an academic, we want to also forge an important partnership between the researchers or the like. If you look at, there was one slide that I did not spend much time. China, alongside developing the capability within the industry itself, they have built up a society of professionals under Chinese Society of Rare Earths, which has about 100,000 members in it. And David, the other day when he was making a presentation at AUSA-MM, he was talking about the combined membership numbers of AUSA-MM, which is Australasian Institute of Mining and Metallurgy, Canadian Institute of Mining, and SME, And number of even South African Institute of Mining and Metallurgy together is only 30,000 or maybe 35,000, isn't it? So that shows how far-sighted China had been. It's important to develop skills at the same time, these going forward. So perhaps.
So perhaps let's look at a counter to that, and a question from Michael Breer, actually, that China isn't the only country with low-cost manufacturing capabilities. What do you see as the chances of alliances? I'm not quite reading his question exactly, but in fact, I'll refer to it. What are the chances of strong partnerships that are going to see this manufacturing happen, but geopolitically in other places? Is this happening?
Yeah, as we speak, for example, India, for example, if I can speak for India, because I know more of India, I read more about India. Indian government has already committed $10 billion into developing their own semiconductor industry, for example. And they're moving at a scale and, at a pace and scale that in the next couple of years, India would become a significant semiconductor manufacturer, not only for themselves, but also for their partners and allies, for example. So yes, it's happening. And also the lithium, now solar panels are currently imported, even India is a case, mainly from China, but now they are giving a lot of emphasis on manufacturing, because that is going to spur up huge employment opportunities, because India is a huge, hugely populated as well, like China. So that brings, if you want to do it anything at a scale and cost comparable to China, perhaps India and Indonesia, which has got that critical
mass. I would have thought also the United States with the Inflation Reduction Act is going to be coming on with some possibilities.
Absolutely, yeah.
Okay.
And if you look at the rare earth, Linus rare earth, $300 million grant is a testament to exactly what they wanted to achieve onshore.
So questions, please.
Hello, hi, Ian Jennings from One Circle. We are at Downstream. We work in the property sector, adopting renewables. And I was alarmed on a couple of points, and I enjoyed your presentation very much. One was really the energy intensity and scale of production compared to what we need to achieve, obviously, the lower carbon world. And that's one part, is sort of, if you think, how little production are we making compared to what we really need for where we're planning to head, the relative energy intensity that will be needed to achieve that processing. And I suppose, and the third thing tied to that, which US was brought up, Linus is an example, but I was astounded on the few mineral reserves in this category in the United States versus its massive consumption. So I'm curious to the extent you would expect the partnerships with the US for security purposes to grow, given it is, of course, an immense beast when it gets going. Thank you.
Yeah, maybe I start off with the energy intensity. So energy intensity is surely going to go up. As I said, as the ore grades are declining, and also the ores are becoming from being simple to complex mineralogies, means the crushing and grinding is a significant portion of it. Unless we find techniques like in situ leaching, perhaps there's no other person that I know in the world who knows better than in situ leaching and its capabilities than Professor Evan Batterham himself. So yes, energy intensity is going to go. But when you look at the life cycle kind of emissions, as I showed, in case of IC engine versus hybrid cars to the electric vehicles, that is the big takeaway. Yes, you may have initially very high energy intensity, but by the time when you compare that technology to this would have significantly reduced emissions over a period of time. Which also means, as you are trying to have more renewable energies into your energy mix, perhaps that also would substantially reduce as we go forward.
I think the answer is not easy.
Yeah.
When you do the sums, there's several questions online. We're going to run out of time, I'm afraid. So let me fire some of them at you, and you can probably read them from there. The question you showed the work of looking at tailings and disused mines and so forth in Australia. In general, what byproducts are available in coal generation fly ash? There's an awful lot of that around.
Yeah, my own colleague at Monash University is one of his PhD students. In fact, I was part of the coal supervision team. He's looking at extracting rare earths out of coal tailings.
Is there not also gallium, I think?
Yeah, so gallium, number of them are there, but the only thing is, for example, as I said, if you are to extract gallium economically, the cutoff grade was 50 ppm. So unless you have that, but again, that could be in ores compared to already finely crushed ground and burnt material. So perhaps it would still make an economic sense. There are many studies where people are extracting number of critical minerals, including even I heard this case where boron and bismuth also were extracted out of coal tailings.
I'll turn to the room, even though there's a few still left online. Please.
Hi, thank you. Jennifer George, I commercialize deep tech. So I was interested in watching those arrows go across when everything was going to be successful with transparency and everything, but we didn't have an element of price in there. So the price really has to, of extracting these things, has to match the the value that we're going to get out of them. Can you think that that kind of technology improvement is there to get that price? And then the other part was that you talked about coal tailings. Well, the high level coal tailings is already taken. It's already has a commercial market. Is the things that you see in the remaining the pond tailings, is that where you see the gallium and the parts per million that you're looking for?
Yeah, I think I'll answer your first question first. In fact, my colleague, David, made a presentation at ASIMM technical talk about a couple of weeks ago. One of the things he said was the price discovery is the crucial thing in all this. Otherwise, everyone would produce everything and then no mineral is going to be critical. But what's happening is there's a lot of sovereign interference in this. If you go back to 2010 rare earth episode, when China restricted the supplies, I think that's when the US in California, they started the Mountain Pass mine, and also at the same time, Mount Weld mine in Western Australia, because the prices were spiking. That time it was a commercially viable opportunity. And then suddenly what happened once these mines came to kind of production and commission stage, more stocks were released and then prices slumped. And then, these miners sort of went bankrupt. And one other important thing, same thing with gallium story. There used to be gallium production that used to happen. I think they were producing about 20 tons per annum. But mind you, most of the critical minerals, they are not going to be needed in huge quantities. If you look at the world gallium production is only 300,000 kilograms. And germanium is only 750,000 kilograms. And we are talking of 750 million tons, when it comes to...
I just want to say that gallium hasn't got a price in the market. So all of this growth that's happened has happened outside of the marketplace. So there's no correlation to what went bankrupt 10, 12, 15 years ago to where the market is now. And it's really important to be able to understand where that pricing is.
That sounds like a good follow-on discussion. We might continue that. Let me draw things to a close, and I'll make 2 points. The first is one of mineral economics. What makes a lot of the energy minerals different is that they're not the prime focus of production. When you look at the things that are the prime focus of production, like copper, then you can actually look at 200 years of data, and you can see that in real terms, the price, plus or minus about 50%, has more or less stayed the same or come down slightly. And this doesn't please a lot of people who say, no, rubbish, it's going to get driven up and it's going to do this and so forth. And I just put 200 years of data on the table and say, no, sorry, technology gets smarter and smarter because grades have been falling for actually 1,000 years or more. We used to mine native copper, by the way. That's how the Bronze Age started, I think. But let's not go there. So the difference here is that they're not a prime commodity that you go out and seek. So I think the rules are a little bit different in terms of the economics. But let me then close formally. I apologize to Julian and Kieran, whose questions we couldn't get to, but they had very much the flavor of, well, how do you make this happen in Australia? And I think the answer is we have to take relatively small steps up the line. We're not going to become battery manufacturers overnight. So Mohan, thank you very much for walking us through and the frameworks. It's a very complex target. It's one that's rather controversial because everyone wants to see more and value add in Australia, but there are all sorts of reasons why it's complex, and you've helped us on that journey. Join with me, please, in thanking Mohan.
Thanks, sir.